To install the pmdarima and pandas-datareader Python packages, you can use the pip command. pmdarima is a Python library designed to automatically select optimal parameters for an ARIMA time series model. Pandas-datareader is a library that fetches data from different Internet sources and organizes it into a pandas dataframe. Installing these libraries provides useful functions and utilities for handling time series data and fetching financial or economic data from online sources. They streamline data retrieval and preprocessing tasks and automate parameter selection for time series models. This text describes the necessary libraries and modules for building and training a long short-term memory (LSTM) neural network model for time series forecasting using stock market data. Here is a summary of the imports and their functions. *math* provides mathematical functions for number operations. *matplotlib pyplot as plt*, used to create various visualizations such as plots and graphs. *keras*, a popular deep learning library for constructing neural network models. *pandas as pd*, provides tools for working with structured tabular data. *numpy as np*, supports handling large arrays and matrices, offering mathematical functions for these structures. *pandas_datareader as web*, enables easy access to external data sources like Yahoo Finance. *sequential, dense, LSTM, dropout, from keras. Layers*, define the neural network architecture with layer types and quantities. *min-max scalar from scalar. Preprocessing normalizes data to a specific range, commonly between 0 and 1, which is crucial for neural networks. *mean_squared_error and mean_absolute_error from scalar. Metrics*, evaluate the model's performance. *train_test_split from scalar. Model_selection*, divides data into training and testing sets for model assessment. *early stopping from keras. Callbacks*, helps prevent overfitting by halting training if the model's performance stagnates. These imports are essential for creating a deep learning-based stock market prediction model that can potentially forecast future stock prices based on past data. This snippet performs the following actions. 1. It retrieves historical stock market data, price information, for the symbol EUR/USD = X, from Yahoo Finance API. 2. It fetches data for the date range from January 1, 2019, to February 1, 2022. 3. It adds 4 new rows to the existing data by creating a new dataframe. This new dataframe includes a date range that starts from the last date of the existing data and extends 4 days into the future. 4. Finally, it shows the tail, last few rows, of the updated data. This code is utilized to acquire financial market data for analysis or visualization purposes. By accessing historical stock market data, one can examine trends, patterns, and make informed decisions regarding stock trading or investments. The extra dataframe with future dates can be beneficial for forecasting or visualization purposes. The data shape attribute is utilized to determine the dimensions or shape of a data structure such as a dataframe in Python. When applied to a dataframe, it provides a tuple that shows the number of rows and columns in the dataframe. This feature is beneficial for promptly grasping the size or layout of your data, particularly when dealing with extensive datasets where manual counting is not feasible. It aids in verifying data integrity and comprehending the structure of the data before carrying out any additional data handling or analysis. This script produces a line plot showing the historical adjusted close prices of a stock symbol. It first sets the figure size to 16 by 8 units and assigns the plot title as Close Price History, with the stock symbol included. The adjusted close prices are plotted against dates on the x-axis and the y-axis label as Close Price, with a font size of 18. The x-axis label is set as Date. This visualization aids in analyzing trends and fluctuations in the stock's historical prices, providing insights for trading or investment decisions based on past price movements. This text describes a simple moving average crossover strategy used for generating buy and sell signals based on the relationship between short-term and long-term moving averages of a financial instrument's closing prices, such as stock prices. The steps involved in this strategy are as follows. 1. Define two windows, short_window and long_window, representing the time periods for short-term and long-term moving averages. In this case, short_window is set to 22, around a month, and long_window is set to 66, approximately 3 months. 2. Set a return_threshold of 0.1, 10%, for triggering buy or sell signals based on specific return conditions. 3. Create a dataframe named signals to store signals, moving averages, and positions obtained from the strategy. 4. Calculate short-term moving average, short_MAVG, and long-term moving average, long_MAVG, using the specified windows on the closing prices of the financial instrument. 5. Generate buy 1.0 and sell 0.0 signals based on the crossover of short-term moving average over long-term moving average and store these signals in the signal column of the signals data frame. 6. Calculate the difference between consecutive signal values to determine the position taken, e.g., entering or exiting a trade, and store this information in the positions column. 7. Print the signals data frame displaying moving averages, buy, sell signals, and positions according to the strategy. This strategy is essential for technical analysis and trading as it enables traders to automate decision-making processes based on moving average crossovers. It offers a straightforward framework for generating trading signals and identifying potential entry and exit points in the market. This approach utilizes the matplotlib library to generate a plot illustrating stock market information. Here's an overview. 1. A figure is created with dimensions 32 by 16. 2. A subplot labeled close price is added to the figure. 3. The AG close dataset is plotted in red with a line width of 2 on the subplot. 4. Two moving averages, short_MAVG, and long_MAVG, from the signals dataset are plotted on the same subplot. 5. Blue triangles, caret, are plotted where the short moving average crosses above the long moving average, golden cross. 6. Black inverted triangles, V, are plotted where the short moving average crosses below the long moving average, dead cross. 7. Finally, the plot is displayed. This method is beneficial for visually analyzing stock market data, particularly for detecting potential buying, golden cross, and selling, dead cross, signals through moving average crossovers. Visual representation of the data aids traders and analysts in making informed decisions regarding stock buying or selling times. This process involves the following steps. 1. The AG close column is filtered from the dataset and stored in the data variable. 2. The filtered data is converted into a numpy array using the values attribute, and then stored in the dataset variable. 3. The length of the dataset is calculated, multiplied by 0.8, 80%, using the math.ceal function to determine the training data length, and stored in the training_data_len variable. This code is essential for extracting relevant data for further analysis, especially in tasks such as machine learning or statistical analysis that require training data for model development and evaluation. Filtering out unnecessary columns and splitting the data into training and testing sets are standard procedures in preparing data for such tasks. This text describes a process for preparing data for training a machine learning model, likely a neural network or a similar sequential model. The steps involved are: 1. Using a min-max scaler for data normalization. 2. Applying the scaler to transform the dataset, scaling the data between 0 and 1. 3. Selecting the training data from the scaled dataset. 4. Initializing lists x_train and y_train to store input sequences and output values. 5. Iterating over the training data from index 60 to create input-output pairs for training. The input features, x_train, consist of the previous 60 data points, while the output label, y_train, is the next data point. Min-max scaler is commonly used in machine learning to scale input features within a specific range. This pre-processing step ensures effective model training and prevents certain features from dominating the learning process. Splitting the dataset as shown in the code allows the model to learn temporal patterns or relationships within the data by providing sequences of data samples as inputs. In summary, this code excerpt is crucial for preparing time series data for predictive modeling, where past values play a significant role in predicting future values. Converting the x_train and y_train variables into numpy arrays is achieved using the np array function. This conversion is beneficial when requiring operations supported by numpy arrays, like mathematical computations, element-wise operations, and vectorized operations. It enhances code performance as numpy arrays are more efficient than Python lists for numerical data manipulation. Reshaping the x_train array involves adding a new dimension of size 1 at the end, transforming each element into an array of size 1. This reshaping technique is commonly used in neural networks, especially when working with sequential data such as time series or sequence prediction tasks. The additional dimension aligns the input shape to the requirements of neural network architectures like convolutional neural networks, CNNs, or recurrent neural networks, RNNs. This process aids in data pre-processing to prepare it for these networks. By reshaping x_train in this manner, the data is formatted to be directly inputted into a neural network model that necessitates a specific shape of input data. This pre-processing step ensures compatibility with the network's input layer, enabling efficient training and prediction. A neural network model is defined using the Keras library with 2 LSTM layers and 2 dense layers. Here is a breakdown of the functionality of each part. 1. Sequential model is created, representing a linear stack of layers. 2. An LSTM layer with 50 units is added, which returns sequences and specifies the input shape based on the input data shape. 3. A second LSTM layer with 50 units is added, which does not return sequences, resulting in an output only at the last time step. 4. A dense layer is added with 25 units. Dense layers are fully connected layers where each neuron is connected to every neuron in the previous layer. 5. The final dense layer with 1 unit is added, serving as the output layer to produce a single continuous value prediction. LSTM layers are suitable for sequential data like time series data or natural language processing as they can capture time-based patterns with their internal memory. Dense layers further process the output from LSTM layers to derive the final prediction. This code constructs a neural network model for tasks like time series prediction, enabling capturing time dependencies for precise predictions. By stacking LSTM and dense layers within a sequential model, an effective deep learning architecture is formed for processing sequential data efficiently. This command compiles a neural network model using the Adam optimizer and mean squared error as the loss function. Here's what this command does. 1. Optimizer equals Adam utilizes the Adam optimization algorithm to adjust the neural network weights during training. Adam combines RMS prop and ADA grad concepts to enhance the learning process. 2. Loss equals mean underscore squared underscore error sets the loss function for model evaluation during training. Mean squared error is often used in regression tasks to minimize the squared difference between predicted and true outputs. Compiling the model with the optimizer and loss function is a crucial preliminary step before training the neural network. This process sets up the model to employ the specified optimization algorithm and loss function, enabling it to learn from training data and enhance performance over time. Training a machine learning model involves using input data, x_train, to train the model and target data, y_train, that the model should learn to predict. The batch_size parameter determines the number of samples per gradient update, with a size of 1 meaning the model updates its weights after each sample. The epochs parameter specifies one complete pass through the training dataset, with an epoch of 1 indicating the model goes through the entire dataset once during training. In summary, this training process involves using x_train and y_train data for one epoch, with a batch size of 1. This process allows the model's weights to be adjusted based on the input data, enabling it to make accurate predictions on new, unseen data. This snippet demonstrates how to use the joblib library to save a machine learning model to a file. The dump function in joblib is used to serialize the model and save it as a file on the disk. The first argument for dump is the model object that needs to be saved, while the second argument is the file path for storing the model. The file path is dynamically created using the format method to incorporate the value of the symbol variable in the file name. This is a useful technique for saving trained models to be loaded and utilized later without the need to retrain them each time. The ability to save models is essential for deploying them in production scenarios, sharing with others, or for future use without the hassle of starting the training from the beginning. This text describes the process of preparing test data for a machine learning model, such as a recurrent neural network, RNN, or a similar model that works with sequential data. Here's an explanation of what the code achieves. 1. It selects a segment of scaled data as test_data, starting from the index training_data_len60 to the end, for testing purposes. 2. An empty list x_test is initialized to store input sequences for the test data. 3. Output values for testing are extracted from the original dataset, ranging from index training_data_len to the end, and stored in y_test. 4. The code loops through the indices from 60 to the length of test_data, preparing input sequences for testing the model. 5. Within the loop, slices of length 60 are taken from the first column of test_data and appended to x_test. Each slice represents a window of data samples used for predicting the next value. This code is crucial for generating the input-output pairs needed for predicting values in the test dataset using a time series prediction model. By structuring the data in this manner, the model can learn to forecast future values based on historical data. This preparatory step plays a significant role in training and assessing machine learning models by ensuring that the input data aligns correctly with the expected output. To convert the variable x_test to a numpy array, we can use numpy's array function. This conversion is usually required when our data is in a list or another data structure, and we need to perform operations that are more efficient with numpy arrays. Numpy arrays support element-wise operations, broadcasting, and vectorized calculations, making them better suited for numerical computations than regular Python lists. By converting x_test to a numpy array, We can leverage these capabilities and access the various mathematical and array manipulation functions offered by numpy. This process reshapes the numpy array x_test by adding an additional dimension of size 1 at the end, transforming it from 2D to 3D. Such manipulation is common in machine learning projects, particularly in deep learning models that have specific requirements for input data shapes. This reshaping likely prepares the test data, x_test, for input into a neural network or other machine learning algorithm that demands a particular data structure. By reshaping x_test in this manner, the intent is to ensure the data conforms to the expected format of the downstream model or algorithm, potentially enhancing model performance and facilitating accurate training and predictions. This text discusses two key operations. 1. Model prediction asterisk. In the first step, model predict x_test is used to predict outcomes using a machine learning model. The model leverages its trained parameters to make predictions on a dataset x_test, typically data that was not part of its training set. 2. Inverse transformation asterisk. The next operation, scalar inverse_transform predictions, reverses the transformation applied to the predictions. This is necessary when the data was pre-processed or normalized before model input, a common practice in machine learning. By applying an inverse transformation, the predictions are converted back to the original datascale. Implementing this code is vital as it enables us to obtain understandable predictions in the original datascale. This facilitates the interpretation and analysis of the model's outputs, as the predictions become meaningful and can be directly compared to the actual data. Consequently, it aids in evaluating the model's performance. This text discusses the process of calculating the root mean squared error, RMSE, between predicted values, stored as predictions, and actual values, stored as y_test. The RMSE calculation involves finding the squared differences between each predicted and actual value, averaging these squared differences, and then taking the square root to determine the final RMSE value. RMSE is a widely used metric in regression model evaluation. It helps measure the alignment between model predictions and actual results, with lower RMSE values signifying superior performance. RMSE enables a quantitative assessment of prediction accuracy. This text discusses visualizing the results of a machine learning model that predicts stock prices. Here's a rundown of the process. 1. The dataset is split into two parts, train and valid. The training part is used to train the model, while the validation part is used to validate the model's predictions. 2. The model's predictions are added to the predictions column in the validation dataset. 3. A plot is created using matplotlib pyplot to display the historical closing prices of the stock and the model's predictions. 4. The x-axis shows the dates, and the y-axis represents the closing price of the stock in USD. 5. The plot includes the actual historical closing prices for both the training and validation sets. 6. Additionally, the plot shows the model's predictions on the validation dataset. 7. A legend is included in the plot to distinguish between the training data, validation data, and the model's predictions. This code is crucial for evaluating the machine learning model's performance in predicting stock prices. By comparing actual and predicted prices visually on a plot, we can effectively assess the model's accuracy and identify any discrepancies between predicted and actual values.